Okay, how are you all? I want to talk about the orthogonal projection. Let's define it as P over finite dimensional spaces, vector spaces, or in this case, even Hilbert spaces. But the main idea is to talk about the orthogonal projection under linear algebra. Now, note that there are two main properties for the orthogonal projection. Idempotence, which means that the square of a orthogonal projection equals itself. This is not what I'm going to talk about. This is not unique to orthogonal projections. Also, oblique projections or not orthogonal projections also satisfy this property. I want to talk about what is unique to orthogonal projection, which is the self-adjointness, namely the self-adjoint of an orthogonal projection equals itself. I want to prove it, and I will use this proof from Gemini in order to demonstrate it to you. Okay, so the space we are over is the Hilbert space, namely it's a complete space, and I can just take the orthogonal decomposition with a subspace, let's call the subspace M, to decompose the space we are over, this Hilbert space, into M and M complement, which is a direct sum, namely there is no intersection between the subspaces, and the sum of the subspace is all the space itself H. Okay, so every vector can be decomposed into a sum of vectors from M and from vector from M orthogonal complement. Namely, take X some vector in H, so I can say that I can decompose it into a vector xm, namely a part of it that lives on M and another part that lives on the orthogonal complement of M, which is M complement. Okay, so xm complement, let's call it. Okay, so if I do this, let's define the orthogonal projection P onto subspace M. So if I take this X that I just defined, so I can say that the P of X equals the XM because it just projects the X into M itself. Now, in order to show that a transformation in general is self-adjoint, namely this holds, I need to show that this holds, namely the inner product between Pxy equals xpy for every two vectors in the space x and y. So let's do it. Let's just open this inner product and show that for every x and y vectors inside the space we are at, we will get that this holds. Remember that in general, let's show you for a general case for a adjoint matrix inner product, it satisfies that what holds is that this one holds. You see that TUV equals U T star V, which is the adjoint. And when we're talking about self-adjoint, we want to show that T equals T star, namely the adjoint, namely the complex conjugate transpose. So we get back to P, and you see that I want to show that if I'm talking about here, it's not P star, it's P. So let's open the two sides and show that they are equal. So for the left side, what I can do is say that Px equals xm, and y itself, I can decompose it again into part from m and part from the complement of m. X I can do the same. So let's open everything up. So let's calculate Pxy. So Px equals just the part from m, so it's this one, and for y I will get this one, namely the decomposition. So I can use the linearity of the inner product and get it to this part. Now, note that everything that is in M, the subspace M, will be orthogonal to everything that is in M complement. Therefore, this one will be 0 because a vector from M is always orthogonal for a vector in M complement. So I can just write here 0 instead of it. Therefore, getting for Pxy just this one, xm, and the part from y that lives in M and not M complement. Okay, this is for Pxy in a product. Now let's look on the other side, on the other part, on the other part of the equation we want to show that is equal. Let's look on xpy in a product. Again, we'll do the same. X can be decomposed into xm plus xm complement. And py is just p is just a part of y that lives on m, so just ym. Again, we'll use the linearity and the first argument for an inner product in a. Let's talk about the real space, so we won't need to talk about something else. So we can just split it into two parts as we did before because of linearity, additivity specifically. So again, we get to the same idea. This one will be 0 because the vectors are from different or from orthogonal subspaces, so it will be 0. So we are left again just with xm, ym. Therefore, we got for x py in a product xm, ym. Now, if we look on this one, pxy in a product, we got xm, ym, and xpy, we got again xm, ym in a product. The conclusion, that they are equal for every x and y. Therefore, I can conclude what I wanted. I can conclude that an orthogonal projection, and note, I'm talking about orthogonal projection and not any other projection. Orthogonal projection over, in this case, Hilbert space, is self-adjoint, namely, it equals its complex conjugate transpose. P star equals P. And this is one of the unique characteristics of the orthogonal projection that a general projection doesn't have to satisfy. Okay? This is it. This is the proof. Thanks very much for Gemini for writing this down. Orthogonal projections are self-adjoint. Thank you all. Thank you for listening, and thank you for watching. And that's it for now. If there are any mistakes or correction, please write it down.